Hello friends, welcome back to the video lecture series of control system. Today we will start with mathematical modeling of electrical system. So outline for this lecture, part 1 is of electrical system. In that, basic elements of electrical systems, equations for basic elements and some examples we will study. In part 2, electronic systems, we will try to study operational amplifiers, inverting versus non-inverting configuration and some examples. In part 1, electrical system. So basic element of electrical system is nothing but resistance, inductor and capacitor. So first we will try to understand equations regarding resistance. So time domain expression relating voltage and current for resistor is given by Ohm's law, that is nothing but V is equal to I into R. So voltage across resistor VR of t is equal to IR of t into resistance R. So if we take Laplace transform of given time domain equation, we get capital V R of S is equal to capital I R of S into capital R. Next is a capacitor. So time domain expression relating voltage and current for capacitor is given as Vc of t is equal to 1 by C integral of current across capacitor, that is Ic of t dt. So if we take a Laplace transform of the above equation, assuming there is no charge stored in a capacitor, then we get capital Vc of S is equal to 1 by Cs into Ic of S. So this is simple expression we get in a Laplace domain. Next is an inductor. So voltage and current relating expression for inductor is given as voltage across inductor, that is VL of t, is equal to L into d by dt of current across inductor, that is IL of t. So Laplace transform of above equation, assuming there is no energy stored in inductor, is capital VL of S is equal to capital L into S into IL of S. So this is simple expression we get in Laplace domain for inductor and capacitor and resistor. So this is the tabular representation of different electrical components, its symbol, then VI and IV relation. These are very important relation because all our electrical systems consisting of RLC only, and if we want to model it, or if we want to find the transfer function of given system, electrical system, then we must know VI and IV relation for each and every electrical component. So this is very important. For resistance, we know Ohm's law, V is equal to IR. From that, VI and IV relation we must know. For capacitor, we just studied capacitor voltage across capacitor is nothing but 1 by C integration of current across capacitor dt, and current is nothing but C dV by dt. Same way for inductor, voltage across inductor is L di by dt, and current across inductor is 1 by L integration of VL dt. So we must know all these VI and IV relations. I'm not saying you just mug up this, but these are very simple. We can prove this No need to mug up and all. And after practicing, we can easily remember all these formulas. Now we will consider one example where two-port network is given. In that R and C, these are the components are given. Output is V0 of t, input is V of t. So we need to find transfer function of given electrical network. So here, if we apply KVL to the loop, we can easily get Vi of t is equal to voltage across resistance is I of t into R by Ohm's law, plus voltage across capacitor is nothing but 1 by C integral of I of t dt. V0 of t is nothing but voltage across capacitor, same formula. Then just by taking Laplace transform on the both side and considering initial conditions to 0, we get Vi of s is equal to I of s into R plus 1 by Cs I of s, and V0 of s is nothing but 1 by Cs I of s. Rearranging both the equations, we can easily get in input side Vi of s is equal to I of s, we get common, and I of s into R plus 1 by Cs, and in output side I of s is equal to capital C into S into V0 of s. So just by substituting I of s in first equation, we can easily get transfer function equation, which is nothing but V0 of s by V of s is equal to 1 upon 1 plus RCS. Here system has one pole, so pole value is what? Minus 1 upon RC. So with this we can easily conclude system stability and response, etc. And second problem is designing problem, where we have to design electrical system that would place a pole at -3. So pole value is given. So minus 1 by RC is equal to -3. From that we get easily one expression, RC is equal to 1 by 3. So if we assume some values of capital R, from that we can get value of C. So here we are assuming R is equal to 1 mega. So 1 by RC is equal to 3. By putting 1 mega value in this expression, we get C is equal to 333 picofarad. So next example, here we have to find once again the transfer function, but bit complicated circuit is given. So here RLC, these are the components where R and L are connected in parallel. So for simplicity, simplifying network by replacing multiple components, so in this case R and L, with their equivalent transform impedance. So instead of RL, we can put over here capital Z, which is a equivalent transform impedance of R and L. So for that we must know what is the equivalent transform impedance of R, L, C or its combination. So transform impedance for resistance, it remains as a R, but for inductor instead of L it must be Ls, and for capacitor instead of C it must be 1 upon Cs. If it is connected in a series, means R, L, C are connected in series, then equivalent transform impedance is nothing but impedance across R plus impedance across L plus impedance across C. So total impedance is equal to R plus Ls plus 1 by Cs. If it is connected in parallel, then inverse of total impedance is equal to inverse of impedance across R plus inverse of impedance across L plus inverse of impedance across C. So inverse of total impedance is equal to 1 by R plus 1 by Ls plus Cs. So this is for homework. Find out the equivalent transform impedance for the following arrangement. This is very simple. By understanding all this basic knowledge regarding equivalent impedance, now we will find total impedance across R and L if they are connected in parallel. So total impedance is equal to, or inverse of total impedance is equal to 1 upon ZR plus 1 upon ZL. Excuse. So 1 upon Z is equal to 1 by R plus 1 by Ls. So Z is equal to RLS upon 1 plus RLS. Now just by substituting Z over there and applying KVL, we can easily get transfer function for given circuit, electrical circuit. So this is one more example for homework. Here also we have to find the transfer function. Here R and L connected in series, and across them capacitor is connected in parallel. So this is one more example for homework. Bit complicated, but practice is must for all these examples. So with that purpose, here homework problems are mentioned. Please practice it on day by day, regularly. If you get any doubts, please ask me on my email ID. Next part is of electronic systems. So here in the third semester, we already studied op-amp in analog electronics subject. So this is inverting, non-inverting, all these kind of configurations we already studied. So in this configuration, transfer function is nothing but minus Z2 upon Z1, and in this configuration transfer function is nothing but 1 plus Z2 upon Z1. If we know these basic transfer functions, then we can easily calculate transfer functions for complicated circuits of op-amp. So for example, here Z2 is nothing but R2 and C are connected in parallel. So if we find equivalent impedance for this RC parallel circuit, so we get value of Z2. Z1 is nothing but R1. So transfer function of whole circuit is nothing but minus Z2 upon Z1. Next is very simple. It is a cascading of two different circuits. So this is the standard circuit. We know the transfer function for this. V out upon V1 is nothing but minus RF upon Rin, and V1 upon Vin for transfer function for this circuit is nothing but minus Z2 upon R1. So here Z2 is nothing but once again C and R2 parallel circuits. So just finding V out by V in and V1 by V in, we can easily get V out by V in. Simple multiplication of this configuration called cascading of two different circuits. Thank you for watching this video. In the next lecture, we will start with lecture 5, which is nothing but block diagram representation of control system.